where were we? So I just fixed the M1s, M1, M2s that we wrote last time. And this is a general thing, right? This was for 3 objects in 1 dimension, right? So we looked here at a system that had 3 balls interacting with each other, and it was a general case, right? Maybe you were thinking that this is just some obscure physical system, just some physics question that is not really important, but it turns out that it's actually very important. Let me just put my video on. There it is. Turns out to be very important because we even investigate atomic vibrations with just this formulation, okay? Like imagine, so before going to atomic level, let me just ask you what would happen if we had this in 2 dimensions. How would the dynamical matrix change? So I have M1, M2, M3, just like before, but now it's in 2 dimensions. So what do you expect to change? It was 1-dimensional, now it's 2-dimensional. Any ideas? Where are you? Okay, degrees of freedom will be doubled. Yes, very good. Very, very good. What do you mean by that? You mean that here it was only moving in x, right? Now they will all be moving in both x and y, right? And if we can still make the harmonic approximation, okay, by harmonic approximation I mean that we will assume that all the interactions are based on kx squared over 2 potential, okay? No anharmonic effects, no x cubed, no x to the 4th, etc. So we will assume that in that case, okay? In that case, you assume that you have something like this. M1 d squared x over dt squared is equal to something that affects it in x direction, all the forces in x direction. So the forces from the second object to the first object in x direction plus force coming from the third object to the first object in x direction, right? So some constant, let me just write it better. Some constant between the first object and the second object in x direction times, this is x1, right? x2 minus x1 plus some constant first object, third object in x direction, x3 minus x1. Am I missing something in this? What do you think? Y components. Why would we get y component in x direction? That's right. We would also get y components, right? Let me actually get to the dynamical matrix. What you would see in the dynamical matrix eventually. What you would see in the dynamical matrix is before you had just 1, 2, 3, right? You had first object, second object, third object, first object, second object, third object. Now it would be first object x, first object y, second object x, second object y, third object x, third object y. Does it make sense? So, and you would have 6 by 6 matrix, okay, and you would have 6 vibrational modes. Are you with me? Yes? Good. So, what if it was in 3 dimensions? 9, right? For example, you have ethylene, right? Carbon, carbon, hydrogen, hydrogen. How many modes would it have?
Depending on whether we take it planar or not.
Let's not take it planar. Let's make it ethane. Okay, it's 3-dimensional. So how many atoms do you have? 8, right? 8 atoms. You have 8 atoms. So this matrix will be 8 times 3 by 8 times 3, right? It would be a huge matrix, 8 times 3, 8 times 3. And you would have how many modes? 24 modes, okay? So 3 of those 24 modes, 3 of them, would have 0 frequency. Why is that?
Uniform translation along axis.
Exactly. So you can take ethane and just move it in x direction. Would it want to bounce back? No, right? Are you with me? No, you are not with me? Okay. Let me remind you something. Let's go back and forth, and see where we go with this. So let me remind you where we were in the coding part. We were dealing with a simpler system, just 2 masses and 1 spring, right? And if you remember, we had these 2 modes. So let me just call it mode, and this is the mode. So mode 0 was something like this, was just this one, right? And it had some frequency. So the strength of the spring, the strength of the oscillation, the amount of force you feel when you do that mode, that vibrational mode, corresponds to that frequency. It's proportional to that frequency, okay? Now, for this one, we have some finite frequency. But for the first mode, mode 1, it wasn't moving, right? That was the problem. It wasn't moving because it was just the mode corresponding to that had 0 frequency. Do you remember that? Now, let's talk about the frequency. Why it has 0 frequency? Because if you look at the mode itself, let's print the mode. Let's print the mode. Where is it? Okay. Let's print square root of omega 2. So you have 2 modes. First one has some finite value, and the second one is 0, right? Let's also print the eigenvectors. And do you see the eigenvectors? The first one is like this, okay, positive and negative. So it corresponds to this motion. The second one is like this, in the same direction. What it means is that you are taking, that mode represents taking the whole structure and moving it all together. Since there is no force stopping you from doing that, that has 0 frequency. Good? Yes? Now, in ethane, I can take the whole thing, I can move it in x direction, and there will be no restoring force. So 1 0 mode comes from there. I can take it and move it in y direction, there will be no restoring force. So another 0 mode comes from there, and I can move it in z direction. Another 0 mode comes from there. Good? For ethane in particular, as far as I remember, and chemists please help me out here, you can move this bond in between quite freely. The bond in between, yes? Because it's a single bond. It's like in a toy car, you have two wheels, and it's not really a good toy car, it's an old one, and you can just keep the middle part, and the wheels would spin again, would still spin, right? So it's like that. So if you rotate ethane, right? If you rotate it, there would not be too much restoring force. So I'm presuming there will be another zero mode for that one. Okay? Not in ethylene. If you have ethylene, then pi bonds are keeping it together, so you can't really move it like this without having a force against it. So you wouldn't have that rotational mode. Okay? Good. My point here was that although we are doing some Newton stuff, some mass, spring and stuff, it's directly related to actual materials, their vibrational modes and whatnot. Okay? Their specific heat, for example, specific heat of ethane would be determined by how many modes it have, right? So all this has connection to thermodynamics. All right? Good. What I did next is to go further with this system. So let me tell you what I mean by that. What if you have a system that has, let's say, 6 atoms, and it has K1 here, K2 here, K1 here, K2 here, and so on. And let's presume that everything is M. How would the dynamical matrix look like for this system? So there are 1, 2, 3, 4, 5, 6 atoms. First of all, what is the dimension of the dynamical matrix? 6 by 6, right? So the first one only interacts with this. Yes, do you have a question?
No, I was trying to draw its mind.
In your mind, yes. Very good. So the first one has an interaction with the second one, for which it's going to get this minus K1 over M. Right? And the second one is interacting with the first one, so minus K1 over M. And in the middle, if you remember, it was K1 over M. Right? But that's the first one because it interacts only with the second one. But the second one interacts with both first one and third one, so it will have K1 plus K2 over M here, and we will have K2 over M here minus K2 over M here. And it will go on like that until you reach. So does it make sense to you?
Yeah.
To everyone? Yes? So that's what this program is constructing. It starts by constructing a dynamical matrix with all diagonals K1 plus K2 over M, which corresponds to all diagonals here. But then you have to change the first one, right? So we have changed the first one to K1 over M. And you also have to change the last one. Are you following?
Yeah.
The last one. And in Python, the last one is minus 1. So you assume that you start from 0. You start from 0, 1, 2, 3, 4, 5. The last one is 6, but it's also minus 1. It goes on the other direction as well. Good? So minus 1 is the last one, and the last one is K1 over M. What do we have here? We say that if we are on the row that is even, for example, 0th row is even, right? then I will write minus k1 minus k1. And what do we have here? Oh, is this wrong? No, it's not wrong. It's just zeroth. So this is zeroth row, and I have minus k1 over 2 over here, right? Because it's I, and this is I plus 1, right? I write minus k1 over m there. But I also write I plus 1 I minus k1 over m because of this one. I plus 1 I. This one is also minus k1 over m. Yes? Good? We are going somewhere with this, I promise. It's not just playing games. Then if it's odd, which means that if we are over here, for example, no, over here, which is odd because it's 0th row, first row. Yes? The first row, then I write minus k2 over m here, minus k2 over m here. Good? Hadia, you are lost? Tell me, what's the...
Can you repeat the even odd?
Yes, yes. So, these are the row numbers, okay? Row numbers. 0, 1, 2, 3, 4, it goes on like that. And these are the column numbers. Column numbers are 0, 1, 2, 3, okay? Let me actually move these row numbers to the left as well. Okay, so what do I tell you? If the row is even, 0 is even, then I write 0 to 1 because I to I plus 1. I write minus k1 over m. But I also write I plus 1 to I minus k1 over m. Off diagonals are symmetric. Okay? Whatever I write here, I write also here. Then I move to the odd one. 1 is odd, right, Hadia? So it's minus k2 over m because 1, 2. And then I write also to 2, 1, the same thing. Yes? Good. So I'm doing it for a particular number of atoms, 6 atoms. Okay. Did I need to explain? Maybe I needed to explain this part. This is just creates a diagonal matrix, and in every point it enters this value n times. Okay. Then let's diagonalize this matrix. Let's find its eigenvalues and eigenvectors. Then what do we do here? Can you tell me? We are sorting the eigenvalues, right? Yeah. We are sorting the eigenvalues. And then what do we have next? What if I write, okay. Is this better? Yes? What do we do here? We are sorting the eigenvalues and eigenvectors accordingly, right? We find the sorted indices and we rearrange the eigenvalues so that it starts from the smallest one going to the largest one. Good. Then what is next? Okay, this is something new. This is interactive plotting. So I have a plotting function here that will just plot x and y's. And x is plotted in a way that I choose a certain mode and I multiply it with sine of t. Okay? So it gives me this nice interactive plot. So I can start with, I can start with 0 mode. Let's go to mode 0. What is the frequency of mode 0? 0, right? And if I move this t, you can see that it goes just, it together goes back and forth. Do you see it? Yes? When I go to mode 1, it's a bit higher. It's not 0, right? By the way, let me remind you that K1 is 1 and K2 is chosen to be 0.1. So what does it mean? It means that these springs are stiff, this one is stiff, this one is stiff, these two are soft. Okay, so let's see how this mode looks like. It's a stretching of those soft springs. Do you see? The stiff ones stay together while the soft ones go back and forth. And that's how you get a lower mode, lower energy or lower frequency mode, right? Good? Mode 2, let's move to mode 2. Still something kind of soft. So let's see what this is doing. This is looking like this. Okay? Again, the stiff ones stay together while the soft ones stretch. Third mode, you can see there is a significant increase, so it must have been must be involving the stiff ones. Let's see. Do you see? It involves the stiff ones. Actually, this time the soft ones never stretch. Do you see that?
Yes.
The soft ones are here and here. So let's move it again. It's only the stretching of the stiff ones, right? Then mode 4, it's a combination. So this one stays together, but the other both soft and stiff ones are stretching. Okay? And finally, the final mode looks like this, and it involves the whole thing moving like this. Okay? Yes.
Can you go through the mode 0 again?
Mode 0 again, yes. Let me guess your question. Why it is moving at all?
Why is it still vibrating?
Exactly.
There's no call back forth.
Exactly. So what I'm doing here is I'm just putting it as an interactive plot, and I'm actually not multiplying this sign with omega. Okay? So it's just I'm putting the same kind of sign on top of everyone, having the same frequency. So for these ones, they actually have zero frequency. A zero frequency oscillation is basically moving with constant velocity. Okay? You are not oscillating. So, any questions? No questions? How many zero frequency modes were we expecting from this structure? One, and we get one, right? Good. Okay. That reminds me. What if I put 0 in here? Do you see? Mode 0 is 0, mode 1 is 0, and mode 2 is 0, right? And all these modes have the same kind of thing, like it moves this one, but nothing happens because this spring is really like 0. It's actually like detached 3 springs, right? And you get 3 zero modes. All right. Okay, this is just for the sake of how you can make a movie out of this. And let's run this. So how does it work? It has this definition, make a movie definition, and bunch of things are happening here, and it basically takes in the values of x and y throughout some time, and it just plots them, and it looks nice. Look, right? I mean, if you need to see your modes at home, you can use this feature. Let me just run this one again so that you get a proper mode. The only problem is that it takes like 5 seconds of your life. Okay? And it keeps moving, it just loops. Okay? Okay, let's look at modes of long chains. Okay? Now I'm talking 200 atoms, let's say. And let me go back to 1.0, 0.5. Everything for a reason. Okay? Yes, we are playing, but we are also learning, hopefully. So what I did here, it's the same code, the same kind of K1, K2, okay? But this time, there are 200 atoms, so there will be 200 modes. And let's actually just plot their values. So this is just their rank, like first mode, 0th mode, first, second, etc., up to 199. And this is the frequency. Okay? Whenever you don't have labels, it's actually the code that I wrote. Okay? Sorry. Okay. Let me show you what happens when k's are equal. Exactly. When k's are equal, you actually get a continuous line. There must be a simpler way to get this line because it seems like there is some formula for it, right? Yes? I mean, let me show you when it's 20. When it's 20, it looks like this. When it's 200, it looks like the curve that you have seen. So some of you do know already how to get this curve. Some of you don't, right? Would it be fun to actually get this curve, derive this curve?
Yes.
There you go. That's the spirit. Before we go there, let me show you also the mode numbers. So mode 0 looks like a flat line. What does this mean? The flat line. It's eigenvector this time, okay? And it's a flat line. What does it mean? You have 200 atoms. Each eigenvector is composed of the same numbers. What does it mean? Yes, you are translating the crystal, right? Not the crystal. It's not the crystal yet. It's 200 atoms, and we are translating the whole thing together. And the frequency of that motion is 0. There's no restoring force for that, right? Look at what happens to the first mode. 0th mode moves together. First mode, what does it look like?
Half of a cosine term.
Yes, right? It's like you want to do this, right? But with the whole 200 atoms. So what you do is you move this one the most, this one a little bit less, this one a little bit less, etc. And then when you reach the center one, doesn't move. Then the next one moves a little bit less, a little bit further, and so it's like this. Okay? How about the last mode, the largest value of the mode? Okay, that corresponds to the whole crystal having as much opposite motion as possible. So it's like you make sure that everyone is vibrating close by. So you are stretching all the springs. That's how you get the highest value for the frequency. Everyone is with me? Yes?
Yes.
Good. So let's actually derive what's going on with this 200 chains. A good way of deriving this stuff is assume that it goes on forever. There's M, 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 K, Okay. And it goes on forever. So what can we do about it?
Assume it's a continuum.
Assume it's a continuum. So there's a problem there. There are two things. One is the periodicity. This is a periodic thing, keeps repeating after every A. So you have periodicity, right? But it also goes on forever, right? Then you have also continuity in here. Is that the right way to write it? Yes? Good. Good. So what we are going to do is we are going to combine these two things into one function. Just like we defined some u's, u1, u2, etc. Do you remember that? Now this time we are going to define some u which will be the same, so that you have the same u everywhere, but we will put a spin on it. We will multiply it with e to the I kx. Okay? So why e to the I kx? Let me explain that. Your chain goes on forever. So why not connect it on the other end? So you have a chain of length L while L goes to infinity. Would it really matter if you connect the ends together? Shouldn't matter, right? Like imagine this, 10 atoms and finiteness, and if you make it finite, it will change. Maybe it will change a lot. Imagine like 4 atoms and you connect them together. That really matters for the system. But if you have 200 atoms, then you connect their heads together, it doesn't matter. It's actually better to explain the infinity, right? Now, L goes to infinity, and what we do is we put on top of this a wave that repeats, okay? So that wave would be e to the I times 2 pi over L times x. Do you agree with that? Because it would repeat itself once you hit L, right? Now, what kinds of different waves can we put on it? We actually can put any n here, 2 pi n over L times x, right? And remember, we can take L as big as we want, right? Hence, you can actually put, if you assume that L goes to infinity, this number is really small. L goes to infinity, this one goes to 0, right? So you can pick a tiny bit of 2 pi over L, multiply it with any integer you want, which means that you can actually take this whole thing, 2 pi n over L, can be a real number. Any real number. And we call it k. Okay? Are you still with me? Yes? So let's see what happened to our chain. We looked at it in macroscopic scale. From far away, it was an infinite chain. Now let's go back and look at it closer again. What we have done to it, we said that, let's say this is u, and this one is going to have u times e to the I k a, because this distance is a, right? And the next one will have u times e to the I times k times 2a, etc. Do you agree with this? Are you lost?
No.
No? How about you? You are lost? No. Anyone who is lost? No. Is it super simple? No, right? We have the right amount of complexity. How about this one? Can you tell me what's this one?
E to the minus IKA.
Very good. And this one? Yes, very good. Now let's construct our motion, equation of motion for this system. So you have k here, m here, m here, m here. What do you have? M times d squared u over dt squared is equal to k times u times e to the ika minus u plus k times u to the e to the minus ika minus u. Yes?
Yes.
Then we can say minus m times omega squared u. Do you agree with this? Yeah? Well, yeah. Yeah. What else do we have here? K times
E to the IKA minus 1.
e to the ika plus e to the minus ika minus 2. Good? So what do we get? This one cancels that one. I have omega squared equals k over m times 2 minus, what is this?
2 times cosine.
That's right, 2 times cosine ka. Okay, so omega squared is equal to, omega is equal to square root 2k over m 1 minus cosine ka. It seems like, we have a problem here. This k and that k are not the same thing, right? So this is k1. Do you agree? Like that k and that k are totally different things from another universe. Okay. What we have achieved the following. As the number of atoms grew, we got more and more modes, right? But they would fit on a curve. So what we achieved is that we have found omega in terms of some number k, and k is a real number. K can be anything. It has infinite values. That's why you have infinite modes. So we have recovered our problem. If we have infinite chain, you should have infinite modes. But luckily, we can actually show those infinite modes as a single curve. Yes? And let's plot this curve. Help me out, please. K is MP arrange. Where should I go from?
0 to pi. Also
0 to pi. Let's go from 0 to pi. Very good idea. Would this work?
probably.
Oh. Look at that. It guessed what I want to do. Although there is something missing here. What is missing? 2 times, actually inside this I should have 2 times k1 over m. So let's go with k1 equals to 1, 0.0, m equals to 1, 0.0. Yes, ready? You get the same curve. Are you happy?
Yeah.
Do you see? You get the same curve. Very nice. So what is this curve? This curve is called dispersion relationship. So you basically have k, which is representing the wave number, okay, and omega, which is the frequency, angular frequency, and you get this dispersion. Okay? What if we kept plotting it? Not between 0 and 2 pi, but go to other values. Like, for example, what if we went from minus pi to pi? It looks like this. What if we have 2 times like this? Keeps repeating, right? Now, why it keeps repeating? First of all, what is this point that we have here?
Maximum allowed name wave number.
Hmm?
Is it the maximum allowed name wave number?
Sort of. Maximum sensible wave number, let's call it like that. So let me tell you what's going on. So that value is pi over a, right? Now what happens? Let's plot it again. Bless you.
It's sort of symmetrical.
Yes. So you have something like this, but then it starts repeating. So this is minus pi over a plus pi over a, right? And then you can see that if you have a ruler that has a length of 2 pi over a, and you put it anywhere you want on the plot, it will point to the same point on the other side. Now there is a good reason for that. Okay? I wish we could have a few minutes for you to recover, to make sure that you understand this part, but we can't stop. So please make sure that you understand this. Okay, let me tell you what's going on. So k can be anything, right? So let's take a value of k that is sort of reasonable. Let's say you have a k that goes like this, okay? K is long enough, short enough, sorry, okay? Now, k is something like, so what do we have here? What is the wavelength, approximately? K is sort of 2 pi over 3a here. Would you agree with that? Because sort of comes back after 3a. Yes? Now, what I'm going to do is I'm going to add 2 pi over a on top of it. What if you add 2 pi over a on top of it? Will it go faster?
going to have an envelope.
Exactly, exactly. So what's going to happen is that, okay, I have to be careful here. Exactly, that's what's going on. So it's going to have something like this. So it will oscillate faster, but whenever it matters for you, because you are interested in u times this function, right? Whenever it hits those points, it will give you the same value. Are you with me or not? No, right? Good. Let's say this point is x, right? Then you have u times e to the I times 2 pi over 3a times x. Yes? Look what happens when I add 2 pi over a. I hope it works. Will it work?
It should probably work.
Let's see.
It doesn't work, but just trust me that it works. Okay. What matters is actually the difference. So let me try it again. Let's say this is x equals to 0. This is x equals to a. Okay, now it will work because I put a special number, magic number a. Now I have e to the I times 2 pi over 3a times a. And it gives me some number, right? What is that number? E to the I times 2 pi over 3. Now what happens if I have e to the I times 2 pi over 3a plus 2 pi over a times a? I get e to the I 2 pi over 3 times e to the I 2 pi. And what is e to the I 2 pi? 1. Do you see you get the same thing? Does it make sense now? Yes? So there is a limit after which you don't want to increase k anymore because it doesn't make sense. And that limit is when continuity hits periodicity. You can have as long wavelength as you want. That's no problem because you are in the continuous regime, right? But as you get shorter and shorter, that wavelength, you hit a point where you start seeing the periodicity. And going beyond that is pointless because you will start repeating yourself. Good?
By the way, during this calculation, where did we use the periodic boundary conditions?
We implemented them by implementing this.
Oh, all right.
Okay. I was planning to talk more about this, about what happens when you go like this, 0.5. So now there is a gap, right? Let me just finish that part next time. We will see why that happens and whether you can recover it or not. Thank you very much.